Hello, this is Professor Gibson and recording about how to do Section 9, Chapter 1 in Math 201 or Business 230. All right, so Chapter 9, Section 1, the title is Correlation. What correlation is the statistical term for relationship between two variables or the data for two variables. So what is correlation? Well, formally, like I just said, it's a relationship between two variables. Data can be represented by ordered pairs, is usually the way they do it. X comma Y, just like you're used to seeing. X is the independent variable, sometimes called explanatory. Y is the dependent variable. All right. We are going to be interested only in linear relationships, which means we're only interested in linear correlation. There's other kinds. It's outside the scope of this class. The vast majority of what you see in statistics, though, is linear. All right. So here's some examples of some correlation, some data, right? See this one here, upper left. If you drew a line coming down, you can see that these data values pretty closely follow a straight linear pattern, straight down to the right. Because it's down, it's negative. This is very strong. Those are closely gathered around the line. Kind of same thing here, except it's up, right? Whoop, a line going up. Data is clustered closely around it. It's positive because it's going up to the right. This is what no correlation looks like. It's just kind of randomly scattered, right? Like you got paint or something on fingertips flicking it against the wall. Now there's a clear pattern here, right? I mean, it follows this arch. Maybe it's quadratic, right? But it's definitely not a line. This is nonlinear. We're not going to care about that. We're not getting into it, right? So there's a correlation there, but it's not linear. We're not going to be measuring it or dealing with it. Okay, so here's the kind of thing that comes up in a typical question. We get some data. We get some X values and some Y values, like here, right? X's and Y's. And in this case, the X's is the gross domestic product, GDP, of some countries in trillions of dollars. And the Y's are the carbon dioxide emissions in millions of metric tons. And maybe, I mean, it just seems logical to me to think that the bigger the GDP, the more manufacturing there is, the more cars there are, the more machinery, all that, probably that the CO2 will be higher. So in other words, these two are probably correlated. Okay? We're not going to come back and do these and these, but it turns out actually in this data set there is a strong correlation. All right. But anyway, so we take those plots and we graph them. These exact ones here we just did, right? GDP in trillions of dollars down here, carbon dioxide emissions here. And if you think about it, it's not perfect, but if you draw a straight line, something like that, that fits the data pretty well, right? It generally follows that pattern. And it does appear to be a positive linear. And like I said, if we actually calculate out the strength of that, it turns out to be pretty strong. Okay, so this is what it looks like to have there is a correlation. Typically, you make the scatter plot. The points do look like they're following the pattern of a line, at least loosely. It means there is a correlation. All right, if they weren't even following any kind of linear pattern, then you'd say there's not one. Okay, so here's the next thing. Correlation coefficient. Okay, this is how we measure the strength of the relationship or the strength of the correlation. Okay, what happens here is the symbols are R is the correlation coefficient for the sample, and the Greek letter rho is the correlation coefficient for a population. Here's this big messy formula. Actually, it's probably the messiest one we've seen yet. And yet, as usual, it doesn't really matter because we're going to use technology. Both the calculators and Excel will find R. Let's talk a little bit about R itself, or rho, really the correlation coefficient. The minimum value is -1, the maximum is 1. If it equals 0, that's when there's no correlation, right? Things just look random spattered. If it's -1, which in the real world it probably never is, means there's a perfect straight line, goes exactly through every point, and it's sloping down, so it'd be -1. +1 would be a perfect straight line, through every point sloping up. Okay? Now, here's some examples. These first two again over here, these two are the perfect ones, +1 and -1. This is a little more likely, right? It's scattered around some. It's still, there's a clear, if you draw a clear line up through it, this is going to be a pretty strong +1. R ends up being 0.81. This one is more scattered, right? I mean, generally speaking, they seem to get higher as you move further to the right. I mean, there's kind of a thing like that, maybe like, somewhere through there. It's not as good though. It's more scattered around, and you can see the R is much lower. It's 0.45. Over here, again, pretty strong, tight pattern right around the line going down, -0.92, very strong, tight pattern. And then this one's just kind of, I mean, I don't see, it doesn't even really seem to go up as you go to the right, maybe by a hair, but this would generally be a no correlation thing. You can see it, the R turns out to be very close to 0 because there's no correlation. All right, so now we've talked about what is correlation and how we measure it using R. The next thing is it meaningful? Is the number R that you calculate indicate that there's a strong enough correlation to be meaningful? Okay. Oh, wait, before we do that, sorry, we've got to do that on the calculator and in Excel. They both do it. Okay, we can do this both ways, calculator and Excel. On the TI-83 calculator, here's your directions. What I'm going to say though, you see this video down here? If you want to do it on a TI-83, I would watch that video. It's about 2 minutes long, and they do a super clean and efficient job of explaining how to do it on your calculator. There's a little bit of a catch to it because you got to turn this diagnostic on. You got to turn it on just one time, so it's set in your calculator, and it'll keep it after that. Here's your steps here. What'll happen is you'll enter your points, your X values into L1, your Y's into L2. This video shows you. Now, the way these work out, just like in Chapter 8, the calculator was easier. In Chapter 9, Excel's much easier. I recommend, see what I'm going to show you here for this video, but I think you'll find Excel's much easier. Here's the command, equals Corel, highlight the Y's, highlight the X's. Mainly the Excel's easier because of the way the data is given to us in MyLabs Plus. All right, so there are two ways. Now we're back to the point where I was making before. There's two ways to check if the correlation is meaningful or significant, okay? The easier way is you can use Table 11. Now, if you go, you're going to want to have this open or pull it up and print it out, whatever. You can use it in your homework. You can use it when you take a quiz or a test. In the course content area in Blackboard, find the statistical tables thing, okay? One of the tables in there is this, critical values for the Pearson correlation coefficient, okay? So if you get a question where you can use this, all you got to do is see whether or not R is bigger than the cutoff shown in the table, okay? Then what you need two things. The table shows two different critical values, right? This one, alpha is 0.05, and then this one, alpha is 0.01, okay? So n is the number of points. So in a question, you come down, let's say you had 20 points in a question, all right? And if alpha was 0.05, then if your R was bigger than 0.444, okay, then you'd, the absolute value of R was bigger than 0.444, right? So, right, the absolute value of R is bigger than 0.444, then it's significant, the correlation's meaningful at the 0.05 level of significance. If it was the 0.01 level of significance, then R would need to be at least bigger than 0.561 to be significant, okay? That's what you do for those. Now there's another way, and it involves hypothesis tests. That's probably not a huge surprise, okay? Now the hypothesis test, in reality, there can be different types of tails and setup and whatever, but in MyLabs Plus, it's always going to be like this. It's always going to do that the correlation, the null is going to be that the correlation coefficient of the population, rho equals 0, and the alternative for these is always going to be that it's not equal to 0. So that's a little bit nice. It makes things a little cleaner as far as learning. It's a little less complicated. It's a t-test, right? So anytime you see one of these hypothesis test or correlation coefficient, know that it's a t-test. Okay. Here's the test statistic. So this is quite a bit different than any of our other test statistics. It's the main difference really between this one and the other ones that we do. This and the wording at the end of it. Most of the rest of the stuff's the same. Okay, the other difference is it's a t-test, but it's not n-1. The degrees of freedom on this are n-2. Okay, now, so let's do an example. The number of hours 10 students spent studying for a test and their scores on that test are shown in the table. Is there enough evidence to conclude that there is a significant linear correlation between the data? Use alpha equals 0.05. There's our level of significance. And right, here's our null hypothesis. Rho equals, right, correlation coefficient equals 0. Here's our alternative, not equal to 0. Here's the way it's going to work. We're asking on, is the correlation significant, right? Is it going to come down to this? If I can reject the null, then the answer is yes, the correlation is significant. If we don't reject the null, it's not. That's very clean, but that's the way they always work. Okay, this one is laid out the way most of them are. They seem to mostly be rejection region questions. Remember, they're all t's. Anytime we have one of these about a correlation coefficient, it's always a t, which means if we're going to find the critical values for the rejection region, tc, right? You're going to get two of it's two-tailed, right? Not equal to. So there's two of them, right? We're going to get plus and minus. In the calculator, it's I and VT, level of significance divided by 2. All right, we need the degrees of freedom. Remember, for all of these correlation coefficient questions, the degrees of freedom is the number of points minus 2, which in this case is 10 minus 2 is 8, right? So 0.05 divided by 2, 8. If you're going to do it in Excel, it's t.inv and then exactly the same on the inside. Either way, you punch these out. Remember, you're going to want plus and minus on these. We get these two, minus 2.306 and positive 2.306. All right. Because it's two-tailed, we get the two critical values plus and minus. Next thing is to calculate the test statistic. Here's the formula for it. We've got all the numbers, right? We've got an R. Oh, wait a minute, I haven't gone and calculated the R. So we need to calculate the R at this point. Now, here's the reason it's easier to use Excel is because of this right here. All of these have that. If you left click on it, it gives you a download. You can download stuff into Excel with a couple further clicks. All right. And it shows up looking like this. So what you do then, the command as I showed you before is equals CORREL, open parenthesis, highlight the Y values, comma, highlight the X values. Corel, this command actually doesn't care which one you highlight first, but some of the ones we use in the next section do care, and they always want the Y first, so I just do them all the same. All right, 0.96014. Okay, so we've now got R equals 0.96014. You see for the test statistic, you punch in R, square root 1 minus R squared, divide it by the n-2. In this case, that's 8, and out this comes. Okay. Now, we're ready to make our decision. So our rejection regions, right? Anything bigger than 2.306, less than minus 2.306, we're going to reject. 9.715, that's much bigger, right? This is much bigger than 2.306, so we reject the null. Remember, when we reject the null, we're rejecting the possibility that the correlation is 0. All right, so that means there is enough evidence at the 5% level, that's what we use for our alpha, to conclude that there is a significant linear correlation. This is the way these are all going to work. If we reject the possibility that the correlation coefficient is 0, we say the correlation is significant. If we don't reject it, then we'll say it's not significant. Okay, that is it for this one. I hope you found that helpful.